Welcome, and thank you all for coming to the second F.Kaiser Spring Lecture. Today's lecture will be given by Dr. Joe Callingham, an Australian astrophysicist based at the Netherlands Institute for Radio Astronomy as the head of the Square Kilometre Array Science Group. This is one of the largest projects in radio astronomy today, and it will allow for many advancements in many different aspects of astronomy, but in particular it's also searching for life elsewhere in the universe by looking at planet formation and searching for biological and organic molecules that could be indicators of life. Further, he's an associate professor at the University of Amsterdam, and his research specializes in radio stars and exoplanets. Today's lecture will be about exoplanet detection, and more specifically about the different techniques that we can use to detect exoplanets, and what these techniques teach us about the diversity of planetary systems, and finally what the possibility is of finding another Earth-like planet out there. So thank you again for all coming, and I hope you enjoyed the lecture.
Thank you. Hello everyone, welcome. Thanks for spending your free time on a Saturday to come and hear about exoplanets and stars. Is everyone okay with my voice at the back there? I'm audible. I don't want to use a microphone if I don't have to. I tend to blast people otherwise. So as lovely introduced, my name is Joseph Callingham. I'm based at Astron and Amsterdam. And what I'm going to do is talk about exoplanets and what it means to find these things and what that could mean for life as we know it. We're a small group, so I'm happy to take questions as we go. Just shoot your hand up and I'm happy to go. You don't need to save it right to the end. Obviously we'll have time at the end. If you have a thought as we go, the point of me being here in person is to be as interactive as I can to 60 people, right? So use that opportunity and feel free to ask questions. Also, I'm Australian, and I know sometimes I can speak fast and with an accent, so feel free just to interrupt if it's not clear as well. Okay, what's the point of me speaking if it's not clear at all to you? Now, does anyone know what kind of special day? Now, it's going to be an aside topic. Do we know it's a special day today? It's Pi Day, yeah! So I thought we'd do a little bit of fun, alright? So I can recite pi to 3.1415926, and that's my limit. Can anyone do better? Yeah, go ahead.
In Dutch,
Well, I can do it in Dutch, sure. Yeah.
denk we gewoon voor de 1, 4, 1, 5, 9, 2, 6, 5, 3, 7, 8, 9, 10, 10, 2, 8, 3, 2, 8, 4, 6, 2, 6, 4, 2, 4, 9, 5, 0, 2, 8, 4, 9, 2, 8.
Okay. I was worried. That's why I haven't hit it. Obviously, up to your rational number, you could go for infinity, right? Until the end of the universe. But congratulations, thank you. So, yes, this is unfortunately an American idea, right? Because obviously it's March 14th, so the Americans do 3.14, hence why it's Pi Day. But I think it's still a little bit of fun. So let's now return to why we're here. We're here to talk about exoplanets. But pi does figure in this, you know. We often try to solve for orbits, and that involves harmonics and conics, circles, and pi always features in all the work we kind of do. So, what about exoplanets? You may think of pictures like this when people say exoplanets. And by exoplanets, I just mean planets around other stars than our sun. It's a very simple explanation, exo being outside, external. You may be thinking of stuff like this. Yeah, you've probably seen images like this. Now, I have to kind of break it down here and make you maybe a little bit disappointed. These are all artist impressions, right? Essentially, astronomers often go to an artist, so once they make a discovery in an exoplanet, and go, this is the kind of conditions we do, and then the artist conceptualizes it like this, and it makes our communication very nice, you know. But I have to tell you the truth, this is not what they really look like in our data, and because you're all an interested crowd, I thought I'd unveil our dirty laundry and show you what they really look like. And this is what an exoplanet really looks like. It looks like a ball. So almost all exoplanet detections, what you're seeing isn't really the planet itself, you're seeing its impact on its host star. Because we can detect the star very easily, and what you're looking at is potential changes in that star to say if you're seeing a planet or not. And so this is a very famous planet. This is what's called 51 Pegasi b, and this is actually the very first exoplanet that was ever detected. And you might be like, what am I looking at here? What is this even going to show? And I'll break this down in a little bit more detail, but this is showing how a star is moving towards or away from you against the phase of the planet. So as the planet goes around the orbit, that's called the phase, you know, so just like the Earth goes around the sun, you can allocate phases, 90 degrees, 180 degrees, 360 degrees. And so this is just showing the wobble of the star. And from that wobble, you can determine mass, and you can determine the presence of the star. And I'll show you how. But this is the very first picture we've ever made of an exoplanet. And it actually won these two guys the Nobel Prize in 2019 for the discovery of an exoplanet orbiting solar-type star, two Swiss astronomers, Didier Queloz and Michel Mayer. So what is the method they're using? And the very first method they used? It's what's called the radial velocity method. And what I'm showing you here now is an artist's impression again, because it's blown up. But what you're seeing is there's say a massive planet near the star, and because of that you have a tug of war. Gravity impacts the star. So even though the planet, say like Earth, is much less massive than the star, it still wobbles it just a little bit. So in the Earth system, in the Earth's sun system, as we go around the sun, obviously we're orbiting, we cause a little wobble in the center of Jupiter. Center of the sun, sorry. and Jupiter causes a lot bigger one. And what I'm showing at the bottom is the way we trace this is by the spectrum. So what we do is we look at different parts of the light, and you look whether something's blue or red shifted. This is exactly the Doppler method. Now, you probably haven't experienced this. If you're ever sitting on the side of a terrace and an ambulance goes by, you have the high pitch and then the low pitch. The same thing's going on here. As the star wobbles towards you, everything is slightly what's called blue shifted. It goes to higher pitch, and as it goes away from you, it gets slightly red shifted. It goes to lower pitch as the equivalent. So it's the same concept. It's just in light rather than sound. When you hear the Doppler shift, that's with light waves. And to put this in the kind of context of what you're seeing, remember that first plot I showed you? This is kind of the exact same parameter space, so you're just seeing the star wobble up and down what's called this velocity space. So I hope that's reasonably straightforward. So you can see that if you have something massive nearby, that obviously makes something shift more than if you have something smaller and further away. Kind of like a tug of war, if you have a big person right close, you can move someone a lot. If you have someone little far away, it's a lot harder to move them. But maybe an easier method of detection to conceptualize is what's called the transit method. And these are very standardized methods. We kind of live in this fantastic world now where I wouldn't say it's easy, but it's becoming standard to find planets around other stars. If you really want to know, we're at this parameter space in astronomy where you can say if it's not. So how do you do this? Well, what you do is you just stare at a star, and you figure out, you stare at it for a very long time, and you just look for these very small drops in its brightness. So this is kind of like, if you ever remember the transit of Venus, or the Mercury transit. So this is now looking at Mercury. Is it working? Oh, maybe it needs to play. Sorry, give me a second. Oh. Here we are. So this is kind of what you're looking for. And this is on very far distant stars. So what you need is actually very accurate, what's called photometry, how accurately you collect that light from the star. And we're looking at like parts per million drops. And this is what space telescopes tend to specialize in mostly. So this is kind of Kepler, if you've heard of that mission before, or TESS is another famous one. And so this is another classic way. And this is just an extension of something you already know. This is essentially just like eclipses, right? Like if you ever had a benefit of seeing a solar eclipse, the moon moving in front of the sun, if you had no other evidence of the moon, this would be a very clear evidence blocking out starlight. And that's just an extrapolation of the idea. Now just imagine that moon is shrunk down to a millionth of its size, and the star is much further away. So that's how two standard methods that we use, kind of what I would call the workhorse methods. Now there's a few others, and I'll come to touch on them a little bit, but I think the interesting problem now in astronomy isn't so much finding planets around other stars. As we know, we did that in the 90s. Where a lot of effort is now going is understanding these planets and what they could potentially be and whether there's a potential Earth between out there. Because you might be thinking, well, what kind of planets do you detect? So remember, I told you that radial velocity method, you have a bias. The bias is if you're big and close, you're going to move the star more. So it makes it easier to find. And the same thing with the transit method. If the planet's bigger and it's nearby, it blocks more of the light than if it's further away and smaller. So all our detection methods are really dominated by finding massive things. And the very first ones we found were these kind of hot Jupiters. As in what I showed you, that first one, 51 Pegasides b, it is a hot Jupiter, as in the fact it's the size of Jupiter, but much closer to the star. It's within the orbit of Mercury. one, we never predicted that in the 90s, but now this is kind of our standard model, is that we have these bias to what we would call short period massive planets in our detection thresholds. And you can see a lot of these now. So this is kind of imaginary of all, many of the stellar systems, not all, because we've got about 6,000 exoplanets now discovered. And what I'm showing you here is the overplot. Is in the background is our solar system. You can see our solar systems are much bigger. And imagine these are all, each one of these kind of little circles here is another stellar system. And you can see the bias we have, right? A lot of them are in only a few day orbits or 10-day orbits. They're not in year-long orbits, right, that we want to get to if we want to say, find an Earth-like planet. And in particular, if you ever go and try and go, okay, cool, we're finding planets around other stars, but what kind of stars are we finding? Because stars come in a zoo of varieties. You know, we've got our sun, we call it a G dwarf. That's kind of like middle of the rung, boring old star, but there's lots of variants. You can have massive stars, like 10 times more massive than the sun. They tend to be blue type stars, we call them O type stars. Or you can be very small, and these are called M dwarfs. And a lot of effort's gone here in finding planets around M dwarfs. So this is an example of an M dwarf here. It's about 10 times less massive than our sun, but 10 times more massive than Jupiter. And so, well, this is kind of the parameter space we're in. And you might be asking, why are we focusing so much on these M dwarfs? Well, if I ever got you to go and count the stars in our galaxy and said, well, how many are M dwarfs and how many are G dwarfs? There is almost 10 times more of these stars than these stars. And it's because they're smaller, they're just easier to form, you need less stuff. And the reason why, that's why we want to focus on these, because like, as much as astronomers love pigeonholing things, a holy grail for any exoplanet astronomer today is finding an Earth-like planet. We want to find something roughly Earth-like that has potential liquid water on the surface. Because the ultimate goal is to say, well, you know, then is there life out there, and all these kind of long-term ambitions. And so if we're going to try and look for Earth-like planets, we probably shouldn't ignore the most common hosts in the universe. And the other one is because it's actually a lot easier to work on these observationally. We're a bit lazy. And I'll show you why. Because imagine I go back to that original detection strategy. Remember, this is this plot I'm showing of this wobble of that star. And this is a hot Jupiter, you know, so this is Jupiter right next to the star. If we did the same thing for Earth and its impact, well, it's just a straight line. You have to zoom in and zoom in. It's a lot harder to do this. And actually really at the limit of our techniques today to be able to say there's an Earth-like planet around a G dwarf. And this, and just to give you some background, is really hard because when you start trying to get that really accurate, other things on the star make a lot of grief. Because we know our sun isn't a static object, right? It's a ball of flame in space, and it boils, kind of like a kettle. You know, you can kind of see these what are called convection zones, and this all produces noise that if we actually try to plot this RV plots, you know, so as in the velocity of this, we're looking for this signal here, and what I'm overplotting is just the sun's intrinsic variability on top. And I'm not saying this is not conquerable, and there's a lot of smart people that are spending a lot of time trying to figure out how do we reduce this so we can say we're finding an Earth-like planet around a G dwarf. But this plot here is trying to give you an idea why we're focusing on M dwarfs at the moment. Because we can do this observationally, and because they're the most common things out there. So we want to ask this question, can we find planets around other stars? And you have to remember, our nearest neighbour, does anyone know the name of it? Our nearest stellar neighbour? Proxima Centauri is an M dwarf. And we've actually found planets around it, right? So this is something we really need to understand, is like, well, you know, there's a lot of other planets around there. So what I'm going to do now is I'm going to focus this talk a little bit on understanding and characterizing these planets, because now we've touched on discovery methods, the transit and the radial velocity method, and now we're going to discuss about like how, once we find these planets, how can we say, is there an atmosphere? Is this potentially habitable? These types of more broader and actually kind of harder questions to answer, because they're not as easy as saying, yes, no, there's a planet, not a planet. And so, remember this M dwarfs we talked about? You know, so this is what we call the conventional habitable zone. You might have heard it called the Goldilocks zone. This is this perfect region that Earth exists in, where it's neither too hot nor too cold, such that liquid water can exist on the surface. And you can do this for any star, right? Now, an M dwarf is much smaller than the sun. So do you think the habitable zone get further away, or does it get closer to the star if you think it's a smaller, less hot star? It gets closer, right? And substantially closer. So to give you an idea, this is a famous TRAPPIST system. This is an Amdorf. Now that habitable zone is within the orbit of Mercury if you put it onto the solar system. So it's right next to the star. And this is good, because guess what? Our transit method and our radial velocity method, oh great, this is exactly where we want them to be. I don't have to stare for 3 years to see 3 transits of the Earth, right, at another star. I can only stare for tens of days, or less than a PhD student lifetime, like in terms of doing their PhDs. But this has some really important implications for habitability, because what I just described, the Goldilocks zone, just takes into account how hot the star is, right? But it doesn't take into account all the other different features of the star. And this is where we're really, at this point in our field, we're really going under a revolution of understanding what does make Earth habitable, and what makes it special, and what do we need on these other planets to make them potentially habitable. And there's a few big ones that we really don't understand, and we need to. Because we know our sun sometimes is not a good host. You can see this massive eruption happening off our sun. This is what's called a coronal mass ejection. What happens is in the outskirts of the sun, what's called the corona, you have some magnetic reconnection event. The details aren't important, but it causes superheated plasma to spill into space. And that can impact a planet, and it can impact Earth. And you might have even hoped for this impact one day if you're in Norway or Iceland hunting in the aurora. You've experienced maybe you want the sun to be in active phase, and we're super lucky that on the Earth we actually have a magnetic field that kind of protects us in the space of this kind of activity. So what I'm showing you now is a simulation of one of these coronal mass ejections hitting the Earth, and the Earth's magnetic field is all shown in the white here. And you might have heard of this event. This is called the Carrington event in the 1850s. This actually knocked out, so just to show how impactful these things are, that knocked out the telegraph network in Europe, caused electric shocks for all the telegraph operators, and caused aurora all the way up to Sydney in Australia, my hometown, and down into Italy, which is exceptional. This is the biggest impact. This is in the 1850s. So why am I focusing? So maybe I should just really say this habitability problem is quite broad, and what we're going to do now is focus on 2 important elements of it. One, how often do these events happen on another star? And you can already tell there's going to be a little bit of a problem, right? So with our sun, we are what's called 1 astronomical unit away, so like many millions of kilometers away. But with these M-dwarfs, you're right next door. So instead of a coronal mass ejection having 1 AU to kind of dissipate, now you're right next to it, You're staring at the furnace, maybe, is the best way of thinking about it. And the other reason is that your cross-section area, you're now much closer, the chance of just being hit is just higher, because you've got less area to cover. And so we need to understand how often these occur on other stars, and we don't really have a good grasp of that. And the other one is, we've never detected the magnetic field on another planet outside of our sun. Even though we've found planets, we have no idea if they have magnetic fields or not. So the problem exists is like, oh, fantastic, we found planets in the habitable zone. But this only is taking into account if this star is a good host. But we know they aren't, that we know they don't do that. So it's potential, even though liquid water could exist on the surface, the stellar activity, or because it doesn't have a magnetic field, meant its oceans are evaporated. It was born with oceans, but after 1 million years, it all disappeared. It all got evaporated by stellar activity. The atmosphere was stripped, kind of like just water on a rock. Just continually just erodes and dissipates. So cool, you found it in the conventional habitable zone, but if we ever send a spacecraft there, all you'd find is Mars, and that would be a lot of fun. We don't want that. And so we need to understand this. We need to understand how often do these types of stars burst like that, and have these planets that we're finding also got magnetic fields that could potentially act as shields in the face of that stellar activity. And as a radio astronomer, I'm going to say the answer's there. So let's think about the electromagnetic spectrum. That's a fancy word of saying light. Light comes in many different frequencies and wavelengths. You know this. Intrinsically, you've used microwaves. You've probably heard of infrared light. You've heard of X-rays. That's all light at just different wavelengths and frequencies. And this is just one way of parameterizing it. Maybe it's a little small for this room. I just like it because we talk about real shapes and real wavelengths in radio astronomy. So what I'm about to talk about is wavelengths on the order of human scale to real scale. If you talk about X-rays and gamma rays, you're stuck in micros and DNAs. So I'm just going to do a little bit of a detour. So let's just park our habitability and talk about radio astronomy a little bit, because one, the Netherlands is very expert at it. We've invested very heavily in it early on. And number two, it comes with some oddities, and I just want to make sure people have fun and understand why radio astronomy is a little bit weird. So when I ask you about telescopes, you probably think of these. You know, particularly in my general public talks, most people think astronomers still do this. That's Galileo. You know, we haven't done that pretty much since the invention of the photograph. You know, and no more really sticking our eye academically to the end of the telescope. We used photographic plates, and now obviously we use CCDs and all types of stuff. Or you may even think of these more modern ones, and there's a telescope you can go and visit here that's similar. The really fancy ones in Chile and Hawaii are these reflective telescopes, use mirrors. You might even think of James Webb, you know, these space telescopes. All these are based on a similar principle, you know, refraction, focusing light, or something like that. The telescope I use is called this one, and it's called LOFAR. If it wants to play, I don't know why all suddenly aren't automatically playing, but okay. It looks a bit different, right? You see a lot of open space. What is this thing? I don't see any mirrors, I don't see any lenses. This is because you can exploit a very interesting principle called interferometry. And so what am I using and what am I seeing here? So these black tarpaulins, if I could pull them back and reveal it, all they are is essentially fancy coat hangers, fancy bits of metal. You know, they're not that more sophisticated than your coat hanger at home, you know, the metal coat hangers. And we operate those and observe those at very low frequencies. So essentially, if you ever get in your car and you turn on your radio, that's the frequencies we're trying to look at the night sky at. So about 150 megahertz, around 100 megahertz for your instance. So you may be thinking, why does this telescope look like this? You know, why has it got this spare land? This is exploiting a principle called interferometry. It's a complicated word, but let's break it down and talk about why we're doing it. So we're going to go on a slight tangent, okay, to just discuss interferometry. And I'll talk about why we do it. And the reason why is like, what is the point of a telescope? You know, what does it really do? And it really is just a very, very fancy light bucket, right? You just want to collect as much light as you can. And the reason for that is if you collect more light, you can see fainter things. And if you have a bigger dish or a bigger mirror, you can resolve things better. You can see things, you can separate things further away. This is like, you know, if you ever imagine standing on well, in the Netherlands you can do this because it's a very flat country. You know, at one end, it's nighttime, a light's coming towards you, you know. Is it a motorcycle with a single light, or is it a car with two headlights? You know, you can use a telescope to resolve it, right? You can go, there we are. It's got two headlights, or it's only got one. This is kind of one of just the resolving principles. And now, I'm just going to introduce some very basic mathematics. I hope I don't scare people away, but this is kind of the way you can express the ability to resolve something. So what I'm showing you here is the resolution, so how well you can resolve something, which is dependent on two principles, and they're easy to remember: the wavelength of light you're detecting divided by the diameter of your dish, and the diameter of your lens, the diameter of anything that you're using for the detection. Now, and the other thing, and I'm not going to detail it too much, you can feel free to ask me, there's a way of expressing this for sensitivity. The people that are super interested, this A times the area. So it just means ability to collect stuff. And so just to show you why radio astronomy, this is a problem for us, is because, well, instead of, does anyone know what the wavelength we naturally see roughly is with our eyes? So optical light, does anyone know roughly the wavelength?
4,000 angstrom.
Yeah, 4,000 angstrom. So about like 500 nanometers, right? So you have to remember, nano is a very small number. In radio astronomy, we're talking about meters, right? So there's 9 orders of magnitude. So 10 to 9 difference between those two things. And so let's just show you. Look at this big telescope on the side. This little cartoon, right? This is about 70 meters, right? We'll say this dish, and they're observing at 21 centimeters. So this big, right? that gives you a resolution of 600 arc seconds. To give you an idea, the resolution of your eye, if you go and look at the night sky with your naked eye and you try to understand if you're seeing a star, it's about 20 arc seconds. So you're like more than 100 times, nearly 100 times worse with your naked eye than what you are with a giant dish, right? And you can see with this little aperture, this tiny little telescope, let's say it's 5 millimeters, you're already doing a lot better, 3 arc seconds at the nanometer. So what do we do in radio astronomy? Or you can do the dumb thing. Well, I shouldn't say dumb, because that's a bit disjointed. You can make a dish really big, right? And then we've done that. There was Arecibo in Puerto Rico until it collapsed. And there's this famous telescope in China called FAST, which is 500 meters. So we went really big. Well, let's build it as big as we can. But look, even at 500 meters, you know, you're only at like 86 arc second resolution versus 20 arc second your eye has. And so we're really at a disadvantage at radio frequencies with this problem. So how can we get around it? And the other problem you have is when you start building things big, you don't build them very reliably sometimes. This is a very famous mistake that happened in the United States at Green Bank in the 80s. This is it, brand new. I think it was only a month old, and then like 2 days later. A lot of money, and I think a few people fired. So we can do this better, and this is what interferometry does. In interferometry, what you do is you kind of exploit an idea where you add up the wavelength and phase. And so this is a very famous telescope called the Very Large Array in the United States. And now what you do is you actually correlate the information. And so what you can say is what light is received here and what light is received here. You just have a big computer in the middle. And what you say is actually your resolution now is set by the distance between those objects. So now you can get away with, you can move these things kilometers away and you can get the resolution that's the same as the naked eye or better. You can spread these over continents. And that's essentially what we've done with LOFA. All these little squares you see here, you can replace them with dishes. And you notice those gaps. What we're trying to do there is exploit this idea that we want the highest resolution we can do, so we can find, for example, these stars and exoplanets, instead of just having a blurry vision. So this is kind of what the principle in interferometry is doing. It comes with cost. I'm happy to explore it more. For the people very interested in the audience, you're technically now taking a Fourier transform of the sky, and I end up spending a lot of time explaining these to grad students. It's complicated, but you win in the fact that now you don't need to build a dish that's the size of Europe. You can just spread them out. You can put a station in the UK, a station in Italy, a station or the heart in the Netherlands, and you can correlate these signals instead of having to, I don't know, dig up Amsterdam, or something like that, and put a big dish in it. All right, that's a little bit the end of the tangent on interferometry. So let's return to this idea of trying to find planets around other stars. And what I would like to do now is have a little bit of fun and see how engaged people are. I'm going to ask a simple question, but sometimes it tricks people. So just think about it for a second. What is the brightest object in the sky at X-ray wavelengths? Does anyone know? The answer is simpler than you think, and I know ex-students can't answer this, or colleagues in the room. Anything? Anyone want to have a guess? The sun. Yeah, the brightest object in the sky, no matter how you try, is the sun. It is bright at all wavelengths, pretty much. This is kind of the way it goes. You ask the same question: what's the brightest object? Optical, infrared. Sun. Thank you for participating. What about microwaves? The sun, the optical. The sun is really bright at all these frequencies. It's the brightest at optical. It's one of the reasons our eyes probably evolved in the way they did, optimizing and parameterizing over where the sun puts out most of its energy. But because it's right next door, even though you've got X-ray binaries, black holes far away, all superheated to millions of degrees, they're very far away. So the brightest thing in the sky still is the sun, even though it's right next door, and most of its light comes out here, not here. But a very fun thing happens at 40 megahertz. So obviously, I'm going to ask you the question now, what is the brightest object in the sky at low radio frequencies? Does anyone know? Yeah. What? I think I heard it. Yeah. Sorry?
Cosmic background.
Oh, close. It's not quite the cosmic background. It depends how you average over it. On the average on the sky, it's not the brightest thing. Actually, is now Jupiter. Which is kind of a profound thing when you think about it. Jupiter reaches out and kind of like steals the crown from the sun at all these other wavelengths. The sun is the brightest thing, except at 40 megahertz. And that's pretty weird. And we didn't quite understand for a while why this is the case. And the case has got to do with actually the presence of Io. So Io is a satellite around Jupiter, the nearest moon, sitting right in the magnetosphere, the magnetic field of Jupiter. And what it's doing is driving really bright aurorae. Jupiter rotates, its magnetic field sweeps over Io, and Io is actually a conductor. And this is kind of like someone plucking the strings of a guitar. The Io disturbs the magnetic field and sets up a circuit and drives these really bright aurorae. You know, so if I could put you on, these are just some of the beautiful aurorae if you could see with your naked eye on Jupiter. And so this is something exciting. It becomes the idea is like, well, obviously, one, you know, we could detect potentially Jupiter away at low frequencies, you know, and number two, it implies something about the magnetic field. And that's what I remember I set up this problem. Like, okay, cool, we can find planets around other stars, but we need to understand, are they potentially habitable? And one of these important parameter spaces is it's got a magnetic field. And so now, we've got a tracer of that. We don't have to go there. We've got potentially we detected at radio frequencies. We can say, is there a magnetic field or not? And could it be strong enough to withstand the violence of its host star? And so, maybe, you know, like we did this fun little trick here. More scientifically, we express this like this. It's a little more boring than dirty pictures. But what I'm showing you here in radio astronomy, which is called flux density, this is the way that you can replace the brightness. Anyone know what this unit is? JY? Jansky. Which is just a term we use instead of watts or something like that. We use Janskys. And this is frequency. And what I'm showing you here is some of the brightest objects in the radio sky. So Cygnus A, Crab, Cassia, these are giant radio galaxies and supernova remnants. But yeah, this is where Jupiter sits. And it's got this very distinct shape, which tells you about the magnetic field. So this is what we want to find. We want to find these other types of Jupiters. There's a problem, but if we go, okay, Jupiter's very bright, but it's also next to us, right? It's next door. Let's now put it at 100 light years. Could we find Jupiter with our best telescopes? And the answer is no. It's just too faint. It's not bright enough. So we need to think of a way to make this emission brighter. And this is what my colleagues and I kind of brainstormed, and there's an easy and quick way to make this brighter so you can learn something. And this is what's called a star-planet interaction. So now, remember I showed you that picture of Jupiter and Io. Now what I've done is I've done something really dumb and simple. All I did was, let's throw away Jupiter, let's put a star there, let's throw away Io and put a planet there. And now the physics still holds. The physics still applies, and you can potentially drive these radio emissions at low frequencies. And so the radio will tell you, is there a presence of a planet? And because of the nature, they're actually quite close. You remember these M dwarfs, that means these things could be sitting in the habitable zone, and you can say, is it there? What is its magnetic field? And is it interesting? And so that's what I'm going to show you a little bit in detail more. And remember, I kind of gave you the idea there was two parameters that we care about in terms of this habitability problem. One is, does a planet have a magnetic field? The other one was, what is the host star doing? Is it emitting these coronal mass ejections a lot? Not a lot? What kind of energy have these coronal mass ejections got? Because remember, these stars are different. Can we scale from the sun? Can we go, oh, the sun emits them every day? It's like saying, you know, like can we scale an elephant to a mouse in terms of how they interact? You know, well, there's similarities, they're both mammals, you know, but an elephant does a lot of different things than a mice does, you know, or a mouse. So that's kind of like the parameter space we're in. It's like, well, maybe we can extrapolate, well, you don't know, you know, so we need to test that. And so one way, and this is again, I'm a radio astronomer, that we want to do this is like, in the ideal world, you do it exactly like we do on the sun. What we do is we block out the stellar photosphere. This is what's called a coronagraph. Corona meaning like trying to observe the corona. And what you look for is these giant bursts. Unfortunately, you can only do this if you can resolve the star or the sun. And they're just too far away. So we can never do this on a star. Even, I mean, like, this is not going to be solved for within 50 years. This is just a real strong problem that stars are far away. So you'll never be able to do what you want here in terms of finding other coronal mass ejections. But we're very lucky at the radio, there's a tracer. So what I'm showing you now is what's called a dynamic spectrum. In the y-axis is frequency, so just like what frequency the emission's occurring, and this is just time, and the color here is how bright something is. And what I'm showing you now is a burst in the radio, what's called a type 2 burst, and this is directly accompanying the emission you're seeing here. So when a coronal mass ejection occurs, it blasts out, and as it travels into interplanetary space, as it goes towards the Earth or out into the solar system, it emits radio waves. And this is what this type 2 burst is. Electrons are just moving very fast at the edge of this shock. And so that's one way of doing this. So it's a very simple thing. You know, what's our goals and what have been a key goal? I won't bother mentioning that. The two key goals that we want to do at radio astronomy is that we want to say, how often do these occur with what energy around other stars? And can we directly measure the magnetic field of another planet? And potentially, you know, its interaction with its host star. And that's what a lot of my group work on. And what do we use to try and find these things? Well, the big one that we use is LOFAR. And what we did is we surveyed the entire northern sky, more or less. And so this is a picture, you can imagine kind of like a Mercator projection of the Earth. This is of the sky. And what I'm showing you here is all these green dots as of 2023. This is a bit of an older plot. We now covered everything more or less outside of these blue lines. Is we just covered the entire northern sky and asked, are we seeing these emission from these stars or exoplanets with LOFAR? So you may be thinking, well, how can you find these things? Because I want to show you something, and this is just dirty laundry a bit, and just giving you an idea about my day job. This is what a radio image looks like. You notice a lot of stuff in here. And we want to find a planet in all this mess. And the question is, what are all these dots? You can see some are smudges, or they look like smudges. They're actually nearby galaxies. And if I actually have to tell you, 99.9% of these are actually faraway galaxies. They're not stars at all. At radio frequencies, we're mostly dominated by extragalactic emission. And this is because when material falls into a black hole, so a lot of these things have got big black holes at the center, they emit really efficiently at radio frequencies. So ironically, even though your eyes, you know, if we look up and we see, open your eyes, you see stars, with a radio telescope you tend to see galaxies far away at redshift 1. So we're trying to find the weird things, which are stars in the radio. So it takes some subtleness, and the way we do it, and this is actually our first detection. I'll just zoom in so you can see some structure of the different types of emission. And this was our first detection here. It looks pretty unassuming. So how can you say, oh Joe, how is this a star, but this not a star? You know? And the answer has to do with, one, we know where stars are. so our optical colleagues, you know, people that observe, they can say exactly where it is. But number two is we exploit the type of emission I described emits very peculiarly, has a particular polarization. So what do I mean by this? I feel like I'm covering lots of concepts. Electromagnetic radiation is a wave, and it can have preference in the way it orientates itself. And you're aware of this because you've probably heard of polarized sunglasses, right? You know, if you ever go on the ocean, you want to have polarized sunglasses that block light, we're using the same concept here. And in particular, nature does this all the time. What we're using is we're exploiting what's called circular polarization. And so you can see these beetles here. If you illuminate it with left-handed, so imagine the light's coming in like this, the vector, or vice versa, you see a different structure on the beetle. You know, nature knows about this very well. This is also true for mantis shrimp at the bottom of oceans. If you're interested, they use circular polarized light. So this is very unique to stars and exoplanets. They tend to emit circular polarization, where luckily our galaxies don't. And so that's where we were so confident about the detection of the star, even though all these, you know, if I turn this into circular polarization, only that thing remains. So, cool, we found a star. What did we really find? Well, what we have to do now is we have to go back to the RV measurement to say, maybe I'll take a step back. When you try to do something new in science, you know, it needs to be vetted. You know, if you make a new discovery, your colleagues are naturally skeptical and go, well, if that's true, Joe, then this has implications X, Y, Z, and I'll go and confirm them or deny them. And the implication is, obviously, if I said there's a planet around the star, that if they go and follow up those traditional methods, like the radial velocity method or the transit method, they should be able to see something. And that's exactly what they've done. This is hot off the press, so it's still relieved. So remember, this is this velocity space against phase, and what you can see now is this little wobble. So I predicted from the radio there'd be a planet in a roughly 1 to 10 day orbit, and my optical colleagues have found a 1.2 day orbit. And so this is where it's very exciting, because now that's the implication of exactly, one, we're using radio now to find planets around other stars, and two, we can determine what it means for the habitability and the magnetic field of it. And so this is just early days where we're sitting. I have to say it's kind of a new region. Maybe you don't take it for granted, but trying to find stars at radio is a bit different. So it's kind of an exciting period to be in. And this is kind of where we're sitting right now. The other one is trying to find these coronal mass ejections. And we got very lucky because just recently, I think we just got the first detection from another angle. Now, what I'm going to show you is not, so this is just to remind people, remember we're hunting for these types of drifting bursts over frequency and time. As time goes on, they drift to lower frequencies. This corresponds to the coronal mass ejection moving out from the star. Once you get that, you can say, oh, how often do these occur? What's the type of energy? What's the density of the plasma as it gets out? And could a planet survive in that environment? And we got this. Now, this star is at 100 light years. That's why it looks a bit more rough, rather than 1 AU. But this is the first detection that was just published in Nature. And yeah, we found the types of conditions. And it's a lot of fun, because then you've got a situation kind of like this. And now, obviously, this is artist impression, I guess. We didn't resolve this with our own stuff. And we got some nice press as well. This is more the international press. It was picked up by CNN and Washington Post and stuff, but it was also picked up by NOS and NRSA and the like. So, I'm just conscious of the time, and I was aiming for about 1:45, so I'd allow some questions. So, what I'm going to do, I'm just going to summarize and wrap up. What astronomers are working on right now, not really discovery space in the sense that, like, it's becoming an industry, it's becoming standard to find planets for other stars. And that's because of these two work-off methods, the radial velocity method and the transit method. And, like, we'll still do these for many more years to come, in particular around G-dwarfs. But a lot of focus is focused on trying to understand these M-dwarfs, because they are the most common stars out there, and we need to understand whether they can be habitable. You know, because if we want to find an Earth-like planet, we shouldn't ignore the most common hosts in the galaxy. And we're tackling that by these detections of the star-planet interactions, because then you can back out from the radio their orbits and their plasma environment, so what kind of space weather it experiences, and the direct detection, so you can get the magnetic field, and obviously this detection of the coronal mass ejections. And so maybe you're thinking, well, what's the future for this field? I'm biased as a radio astronomer. The big inference is something that's called the square kilometre array, which kind of loops with the star. This is a $1 billion telescope being built in the deserts of South Africa and Australia by an international organisation, including the Netherlands, but the United Kingdom, France, Germany, South Korea, India, Canada. We're all putting down these medals, and that's super exciting. In the next couple of years, you will see the first data coming from this, and I hope we'll be able to see more of these coronal mass ejections and potentially the first really direct emission from a planet around another star. So we can begin to answer and understand, are there Earth 2.0s out there, and could we potentially find anything more interesting from that? Thanks for your time, and happy to take any questions.